Okay, so again, looking at chapter 8, since that's your hardest piece for AP so far, we reviewed in the other piece, but it comes up here too, a Taylor polynomial. If I'm degree n. So that would be P sub n of x is f of c, my center, plus f prime of c over 1 factorial times x minus c to the 1, plus f double prime of c over 2 factorial times x minus c squared, and so on, f plus f to the n derivative of c over n factorial times x minus c to the nth power. Some other things that come up with this. For example, they will give you a question that says, what is f, well maybe they'll say, hold on, they'll say that you have a Taylor polynomial centered at x equals 5. What is f triple derivative of 5? And they will actually have given you a Taylor polynomial. So maybe they gave you P7 of x and they wrote out all the terms for you. And they want you to use that to figure out the triple derivative evaluated at 5. Well, as long as that's at 5 and you're centered at 5, that's good. I could go out, if you notice, the type of derivative matches the degree of the term. So I could find the term with x to the third because I want the third derivative, and the coefficient of that term is going to equal the third derivative at 5 over 3 factorial. So I could find that number, whatever that is, set it equal to the triple derivative of 5 over 3 factorial, and this is what I'm trying to find. So algebraically, I could think about that number over 1. I could cross multiply to get 3 factorial times whatever that number is, and then come up with f triple prime of 5. So that comes up quite a bit. Okay. Something else that comes up quite a bit that I know we've struggled with are using the remainder theorems to talk about error. So if we take a look at error, there are two types that you're going to see. One deals with the alternating series remainder theorem. And to use that, you must have a convergent alternating series. So if you go back to your flip books, you need to talk about alternating series test and make sure all those conditions are met. Or sometimes they're nice enough on free response to just tell you that they are met, and that's nice. So if that's the case, then the error is just in absolute values, the difference between f at the number, the actual function at the number, and p sub n at the number, the Taylor polynomial. And that's the case whether we're doing alternating series remainder or whether we're doing Lagrange error bound. So then that error, which is again the difference between the real value, f of the number, minus the value I get, p sub n of the number if I use the Taylor polynomial, is going to be less than or equal to a sub n plus 1. This is just the next term in line in the series. Okay, so that would be alternating series remainder theorem. Then we also have Lagrange error bound. And that's the same sort of idea. But Lagrange error-bound talked to you about the difference, again, between the real value of the function and the Taylor polynomial at those same numbers. It's going to be less than or equal, and then it was an absolute value. And since we were taking a look at a Taylor polynomial, it kind of mirrored the format of a Taylor polynomial. But it also used this idea, if you notice, for alternating series, looking at the error for the nth one, dealt with the next term in line, dealt with n plus 1. Oops, that kind of made it ugly. Let me take that off so it's still easy to read. This is going to happen here as well. Looking at the nth degree Taylor polynomial, the next one in line would be f to the n plus 1 derivative. And that's evaluated at z. We'll talk about what that means in a second. Over, again, next one in line, so that would be n plus 1 factorial times out to the side x minus c, and again, next one in line, n plus 1 power. And all that's in absolute values. And we need to talk about what that whole f to the n plus 1 of z piece was. So this portion where f to the n plus 1 of z in absolute values is the max value of f to the n plus 1 of x, the n plus 1 derivative, but between, and it's in absolute values as well, between the number that you were interested in and the center that you wrote your polynomial around. Okay. If AP comes out and says, hey, use Lagrange error bound, then do it. If they come out and say, hey, we need you to relate this to alternating series, then come out and do that. If they don't tell you anything and they just say, can you prove to me that the error in using this polynomial to approximate the real function is less than some number, well, I would take a look at the series they give you, and if the series alternates, then I would try to do alternating series remainder. But if it doesn't, then I would probably do Lagrange error bound. Okay. All right.